So this is what I'm going to talk about. It's an IV&V topic, so I'll give some background information and then talk about the BBN approach that we developed and some preliminary results. So as I said, that's the research team. And so we were talking a little bit earlier this afternoon about IV&V and what it is and what we do. So the main characteristics of it, first, it's independent from a managerial and technical and a financial perspective. And it's an analytical approach that we use. It's kind of a broad set of analytical tools that we use to evaluate the software for correctness and completeness. So it's not strictly a software discipline. It's rather a systems engineering discipline, but our focus at the NASA IV&V Center is on the software aspects of the system. So the scope for the IV&V Center is all of the NASA mission critical software. So that includes the HEO as well as science missions. The key information sources that goes into an IV&V project are the IV&V technical framework, which is the set of processes and tools that we use, as well as the developer artifacts, all of the artifacts that are produced in the development process. So there's, as we discussed earlier, because there's so many candidate projects for IV&V and such limited resources, it's necessary to determine first which projects are those that are the most deserving of IV&V. Certainly they all deserve it, but it has to be based upon some assessment of criticality and risk. And then once that's done, it's necessary to divide up IV&V resources among the projects, and then within a project to divide up the IV&V resources among all of the various analysis things that you could do. Because the set of things you could do even for one project is essentially infinite. You can never do too much verification. So the long-term project that we're working on is to use complete architecture information to identify and evaluate risk and to facilitate the IV&V planning process. Architecture information has certainly always been used by IV&V analysts to do the IV&V, but it's difficult to incorporate it into the early life cycle planning process because there's not a lot of architecture information available. The information that's available is mostly development view kinds of things, and as a result, the planning process has been more focused on that aspect, in which leaves out a lot of the architecture information that is going to be accounted for in the development. So the goal of this process, this research line, is to incorporate the full architecture in the early life cycle process. And so the result of that is to identify the specific high-value assurance objectives and specifically things that aren't going to be visible just by subject matter expert review of requirements, and also to develop a reliable and repeatable process for doing that. So the previous work that we talked about here last year was we developed a mechanism to capture architecture, at least at a high level perspective, really early in the project planning process, using all the available artifacts to capture all the architecture views, and we did that using a 4+1 model, as well as the cross-cutting concepts such as technical budgets. And based on that identification of the architecture, then we extended that to an approach to identify the set of risks associated with each of the architecture elements that we identified. And so that set of risks leads to the analysis work that IV&V is going to do. So this is the general overview of the scoping and planning process, particularly for the early life cycle. So the logical flow is first we determine what the architecture is, then we determine what the risks are associated with each of the architecture elements and cross-cutting concepts, and then from the risks we can identify assurance objectives which are a set of questions or activities that the IV&V analysts are going to do to reduce uncertainty with respect to the risks. So we can category can call risks the things that can go wrong, which can be either operational or development. So development risks would be coding errors, testing errors, and operational risk would be the malfunctions of the system in operations, that things that aren't directly development related. In assurance objectives, as I said, they flow from the risks, and those are the set of things that the IV&V analysts are going to do to add assurance that the risks are controlled. So when we do those activities, we don't eliminate the risks, but we eliminate uncertainty with respect to the risks. So the risks are typically hierarchical. So a top-level risk might be the failure of some architectural element. So that could be a scenario that doesn't progress to completion correctly, or it could be a failure of another architectural element. And then supporting that are things that lead to that risk becoming manifested. And we want to decompose that down to the level where we can address the root causes of risks. And in some cases, a single supporting failure can cause an architectural element to fail. In others, it's going to take multiple failures together to cause that. So the risk the approach is that's used by the IV&V Center is the standard NASA risk cube, where we consider both the consequences of a risk and the likelihood that the risk will become manifest. The consequence is in terms of severity, and that's typically on a scale, usually 1 to 5. And likelihood is based on a similar kind of a scale, but the likelihood is determined from not from analysis of the consequences of it, but from the indicators of that risk. So the indicators can be, and we'll look at in a minute a little bit more detail of them, but the indicators are things, characteristics of either the product or the process to develop the product that contribute to the risks or that reveal information about the risks. It's essential that the scoring that's done is accurate, both with respect to what the consequences are and the likelihood, because if they're not accurate, then it's going to result in dilution of the IV&V resources, putting resources where it's not going to give us the most benefit. And it's important that we identify the highest risk elements so that we can ensure that they get the proper attention. So this is a standard risk square that we have. You see it in both formats with either thing on the X and the Y coordinates. But the way that we're showing it here is with the consequence, which comes from analyzing what happens if the risk is manifest, and on the bottom, and then on the side is the likelihood, and the composite score, the product of those, is the overall risk score, and the red is bad and the green is good. So when we're doing the risk analysis, the consequence work is pretty much dependent on the system, and although it can be laborious, it's not going to be particularly controversial. The likelihood, on the other hand, is more difficult, because we're trying to decide what's the relative probability using this 1 to 5 weighting of this particular bad thing happening compared to all the other bad things that can happen. And that's a little bit more challenging, in which led to this work. The traditional approach to doing the likelihood scoring is to use a set of basically adjectival kinds of characteristics in order to develop a numerical score. So we can divide them. The set that are here, the 6 that are here, the set that are currently being used. So from the environmental perspective, is complexity, robustness, and testability. where complexity is how complex the function that's being implemented is, not necessarily the code. Robustness is the ability of the system or of that function to deal with uncertainty, and then testability is obvious. So those are the operational environment kinds of characteristics that deal with likelihood. And then the process characteristics have to do with the software development process, the amount of innovation in the process, the heritage, and the information assurance are the characteristics that are currently being used. Those 6 characteristics have evolved over the years of the IV&V Center because they've been found to be pretty good indicators of whether something is likely to have a problem or not. The way that they have traditionally been combined is just computing a score based on a weighted sum of the scores on the 1 to 5 scale of each of the 6 characteristics. So it's just a linear combination of those 6 things gives you the likelihood score. The problem with that is at first it tends to push things towards the middle, and a second it's not typically standardized across the projects. So what we're working on with the Bayesian belief networks that we'll talk about next is a way of capturing the relationships among those in this case those 6 indicators, although it's certainly not necessary that we use that 6, in a way that accounts for the nonlinearities in the system, and the fact that sometimes some of them kind of cancel one another, and other times they reinforce one another. So in order to do that, the method that we developed uses a Bayesian belief network. So a Bayesian belief network is a probabilistic approach to combine evidence. So you can use a belief network in 2 main formats. You can use it to reason forward from a bunch of evidence to predict the likelihood of what's going to happen, or you can use it using Bayes' theorem reasoning backwards to take some event and determine and determine the likelihood of each of the symptoms that contributed to that. So if you can use that, in other words, using it for diagnosis. So something bad happens. Why did it happen? That's the Bayes' theorem reasoning backwards. And the format that we're using it is, if one of these bad things happens, then what's the likely consequence of the system to fail? So it recognizes in this approach that the risks, the manifestations of the risk could be treated as a random variable with a probability density function that depends upon those risk indicators that we looked at on the previous slide. So this allows explicit modeling of the nonlinear behavior, and it gives us a way to exploit the expert opinion in a nice, clean format. So this is the basic structure of a node of a belief network. What the network represents is a causal relationship between 2 parameters that give us a random variable with a particular probability density function that depends on the values of those 2 parameters. And we can cascade those to form a network where the outer nodes are the inputs, and then the inner nodes are the causal relationships that work together. So this is the prototype network, a diagram of the prototype network that we developed for the likelihood estimation. So we have is that these 2 nodes are the 2 main categories, the environment and the process, and then the 6 indicators are the inputs to those. Now the indicators can be a point value, or they can be a value with a tolerance. In the tolerance, and if you do that, then you can just use that as another random variable. And then, of course, those go together to create a random, the 2 inputs for the likelihood node, and then the output of that is a random variable that has a PDF that depends on that. So then we can evaluate the network using a Monte Carlo approach, and in order to do that, we need to have functions for each of the PDFs for each of these, in this case, those three nodes: environment, process, and then the likelihood. Oh, it went backwards. So the development of the node PDFs, each node, as I said, maps a set of inputs to a PDF, and it's not practical to calibrate for a system like this, to calibrate the network empirically, because it would require, in this case, thousands of software projects of the same kind in order to have a meaningful calibration. So instead, we do it using expert opinion. So essentially what the network is doing is allowing us to capture knowledge from people that have a lot of experience. And the way that we capture the knowledge is using a simple PDF editor. And so what it's doing, if I look at the next slide, the PDFs are either a surface if there are two inputs, or a hypersurface if there are three. And so what we're doing is developing control points for trapezoidal probability density function by locating key landmarks in that and boundary conditions, and then work back and forth between the editor where we enter the PDFs by stretching the circles on the diagram. These little circles, you can grab those with a mouse and move them to sketch the PDFs. So what each of these is, this is the PDF that we expect if we have that three sets of inputs. And then we can again switch back and forth from the editor to the diagram until we get the PDF that makes sense. And then that whole network is evaluated using a Monte Carlo model. The IV&V Center uses MATLAB. We implemented it in MATLAB. And so for each Monte Carlo trial, you generate a random input, a random number using the PDFs that come out of the node to generate the inputs to the next succeeding node, and then do the same thing at the bottom level to get the likelihood score. And so we do that for a whole bunch of trials and get the statistics of the output. So we use the research team for the preliminary work to develop the node PDF tables, and we did it using the spreadsheet that is already being used for the planning. So it doesn't take any extra work for the planning thing. We'd use the exact same spreadsheet to do the inputs to the BBN, and it allows us to do that without doing any extra work. So this is an example of their spreadsheet for a hypothetical project with a set of capabilities. And so we have the scores, and in this case it's set so that we have the estimate for the score, and we put it on a 1 to 10 scale instead of a 1 to 5, just because it gives us a little bit more discrimination. And then a tolerance above and below. And so there's going to be a separate Monte Carlo run for each of these capabilities. And this is the output of the nodes for one particular run. And so these are histograms that just shows you, using the Monte Carlo, what the PDF is for each of those nodes. And then that just shows you the expected value and the other statistics of each of the nodes. So the input data was easy to collect because they were using the same process that's been used in the past. We found that calibrating it was not that difficult a process of just iterating with those two diagrams, and it allows us to model the nonlinearities and to recognize the uncertainty in a nice, clean way. So in the future work is to continue to implement this on actual IV&V projects and refine the calibration based on project results. So that concludes the pitch. If there's any questions. Did okay?
Questions? You were using a mean and variance, but is there any indicator that any of the data is actually normally distributed? Or is that just because it's a relatively limited range of things, it's close enough?
Well, we're not assuming anything is normally distributed. That's, we're sketching the probability density functions using that trapezoidal PDF. So you can approximate a normal if that's what you think it looks like, but you don't have to. But any random variable has a mean and a variance, not just normal random variables. A uniform random variable has a mean and a variance. Those concepts aren't defined in terms of a Gaussian distribution. They're based on just the notion of distribution.
Well, there are PDFs that neither one of those actually exist, but there are more exotic PDFs where those numbers don't actually exist. So, but they're probably outside the scope of this.
So any other questions? All right, thanks.
Other questions? Okay, thank you.
Right.